All right, everyone, welcome back. So today we're going to start off by doing a lab, and then we'll talk about what you see after the lab. So you're going to end up going into the lab and taking some data, and then we'll come back and then figure out what that data is telling us. So let's get right on to it. So what you're going to see today is we're gonna figure out what the speed of sound is. We're going to measure the speed of sound in class today. So if you don't already have the lab sheet, you want to go ahead and make sure you get that. If you need to pick it up from the tray, or if the substitute hasn't handed it out, please go ahead and get your lab sheet. So what you'll do today is we're going to end up having this really big graduated cylinder. So here's a big long tube, okay, and there's our graduated cylinder. Okay, and you're going to fill it up with some water. So we'll make sure that the water is turned on. So we'll fill it up with some water. And then what you're going to do is you're going to stick a PVC tube into it. Okay, now you're not going to let the PVC tube go all the way in, but you're going to stick a PVC tube into it. We're going to call this our resonance tube. Okay, resonance tube. Then you're going to grab a tuning fork. Okay, so a tuning fork, and you're going to hit the tuning fork on something nice and soft. So something like using the mallet that comes with the set of the tuning forks, or you can hit it on the bottom of your shoe. Please don't hit them onto the tables or anything hard. It makes a really bad clanging noise, and it could also chip the tuning fork, making it change its frequency. And we need those frequencies to be as precise as possible for this lab. So what you're going to do is you're going to make that tuning fork sound, and then you're going to put the tuning fork above that was supposed to be an arrow, above the resonance tube, above the PVC tube. And then you're going to move the tube up or down, depending on, you're just going to move it up or down, and you're going to listen for something strange to happen. Okay, so it could go up, could go down, but what will eventually happen is that you're going to end up with a resonance. So if you've ever blown across the top of like a 2-liter bottle and made that noise, right, you had to blow exactly at the right speed. This is something very similar to that. You're going to move the tube up and down until you hear a really loud resonating noise coming from the tube itself, and you should be able to really pick it out. Now, sometimes it'll be a little difficult to figure out whether it's your tube resonating or someone else's tube resonating, but I think you guys can figure it out. So what you'll do is you'll find that exact point where it's resonating, and then you'll measure the part of the tube that is out of the water. All right, so this is going to be the length of the air column, is what is labeled on your lab sheet, the length of the air column. You're going to make a note of what frequency is being used, right? So we'll need to know the frequency, and we'll need to know the length of this air column. And that's all the data that you're going to take. The rest of the data, or the rest of the stuff, is going to be your calculations, except for one thing. You'll need to know the temperature of the room. So you can have the substitute take a look at the thermostat, or you can go take a look at the thermostat, but you'll need to know the temperature of the room. And there's a place to do it in Fahrenheit, and then you'll need to actually calculate it in Celsius. So you can get on your phones or something and figure out what the conversion is to get from Fahrenheit to Celsius. I'm pretty sure you can just go Google it, and they'll do it for you. So you're going to get into the lab and go ahead and start taking your data. So what we'll do right now is we'll just pause this video, and you'll get in there and you'll take data with a couple of tuning forks, get some measurements, find the temperature, and finish that calculation. So we'll pause right now, and I'll see you in a few minutes. All right, everyone, welcome back. So what exactly were we looking at? So last class we had talked about standing waves, right? Standing waves on strings, and how waves that were going out and waves that were coming back in were interfering with each other, and that is the reason why we can get this wave interference, and we can get some standing waves in a closed thing like a string. Well, it turns out that sound waves can do the exact same thing. So if we're thinking about a tuning fork, right? A tuning fork, there we go, kind of, there we go, tuning fork. So as the tuning fork vibrates, right, you hit it, and we know it vibrates. This thing goes back and forth, back and forth, back and forth, back and forth. So if we were looking at things like molecules in the air, right? Molecules in the air. We'd have a whole bunch of molecules in the air right here. We'd have a whole bunch of molecules in the air right here. And we'd have a whole bunch of molecules in the air right here. Well, as the tuning fork hits these molecules, that transfers that energy out to the next molecules, which transfer to the next molecules, which transfer to the next molecules. So this is a sound wave that is propagating out. But this is a longitudinal wave, like we saw in those first notes. It's a longitudinal wave. So we end up with a high density area or a compression that transfers out this way. So it's more like a compaction of molecules. So if we go back to this thing right here, then we are sending waves down the tube, and the tube is going to be kind of a confined area. So the wave is going to come down, it's going to hit the water, and it's going to bounce back. So we're going to have waves coming back out as well. So this is an area where we have sound waves going in and sound waves coming out, and so we end up with interference. So what does that interference look like in a tube? Well, take a look at this picture. So let me get the picture in here. Give me 1 second. All right, so take a look at this picture here. So what does this look like? Well, we have looks like areas where we have quite a few particles, right? Areas where we have quite a few particles. This would be kind of areas where we have really big pressure. Okay, big pressure, which means those particles are really near each other. Then we have these areas that kind of have lower than normal pressure, and that's the areas that are in between these areas. So in our terminology, that's called a rarefaction. It's a rarefaction. And then we have this other graph right here. Notice how the pressure graph looks like a nice sinusoidal graph, right? This other graph was just talking about the displacement. So it turns out the molecules don't actually travel from all the way to the left side to the right side. They're going to just sit there and vibrate back and forth like what we know waves do. They're just vibration. So this is actually a still image from an animated GIF. So I want you to take a look at what this looks like. So watch this. All right, so what did we see? So if we focused on one of these little red points right here, then you would have noticed that these little red dots didn't actually travel from right to left. All they did was kind of just go back and forth, back and forth, back and forth. So that's what this graph down here was talking about, is the particle displacement. So it'll either go to the left or it'll go to the right, but it's just going to keep oscillating back and forth, back and forth. But if you really take a look at these graphs look like the things that we actually saw on the string, right? The harmonic level on the string. But if you notice, one side of it seems to be fixed in place, like what we had on the string, but the other side is completely open and it goes back and forth. So one side is what we would call a node, and the other side would be what we call an antinode. Antinode. And that's what happens on a pipe like this. Okay, but it's a pipe like this where it's closed at one end and open at the other end, and it is open because this is the thing that was causing the actual waves to go back and forth, back and forth. So this is what we would call an open pipe or an open tube. So if we go back to our tuning fork here, we have an open tube here as well. Right, we have closed off one end from the water, and then we have an open on the other end for the sound to go in and out. So if we take a closer look at that tube, right, what we'll find is that the first harmonic is a type of standing wave that shows a node right here and an antinode, okay, antinode right here, so it's completely open. And we're going to draw it in that looks like this. So we have, hold on, let's see if I get my stylus to work. And I'm kind of drawing it in as the dotted line on the other side because it's going to oscillate back and forth. So that looks weird, and it's actually on the on your lab. The top right image of your lab kind of shows the same thing. It doesn't show the dotted line, but it shows two solid lines going like that, out like that. Now, what is this showing us? Well, it's showing us this image, right, where we have a lot of particles moving around, and they're constantly changing. But it's represented in like one of these sine graphs down here. So what we're seeing is a high area where we have pressure versus a low area where we have pressure. So here is particles are not moving at all, and here they're moving quite a bit. and we have a little bit of movement going on in between. But this is what we would draw in as a standing wave, even though it's not really representative of the particles, it's more representative of how they're moving. It can get really confusing because what's actually happening is this guy, right? That's what's actually happening. If I can get this thing to circle, there we go. That's what's happening inside the tube. The particles are vibrating back and forth. But it would be really tough to sit here and draw all the little particles to go in here, and especially drawing them as they would move, so it'd keep changing. So we draw it like the sine graph thing that we have been doing with the strings, just to make our life a little bit easier. So let's figure out what's going on here. How many wavelengths is this? So if I put it maybe this way, you might be able to tell me that. So how many wavelengths is that? Well, we know that a wavelength has to go from point of the wave back to the exact identical point of the wave, right? So this would be one wavelength, one lambda. Well, how much of that do we have over here on the left-hand side? That'd be like if we chopped it right there. So how much of the wavelength do we have? Well, we only have a quarter. We have a quarter of a wavelength. So that means the thing that you measured, that length of the air column, that's actually a quarter of a wavelength. So if we wanted a wavelength, we wanted a full wavelength. If this equals L, the length of the air column that you measured, that means a wavelength would have to be equal to 4L. It's kind of similar to what we had on the fundamental harmonic for a string, where we ended up with 2L. We would need 2L in order to get a full wavelength. So in this case, it's 4L. So the next thing that you'll have to do on your lab for your calculations is to figure out what your wavelength is. Your wavelength would be 4 times that length of air column that you calculated. From there, you have enough information to figure out the speed of sound. So if we are looking for the speed, then we have velocity is equal to wavelength multiplied by frequency. So you've seen that from last time. So you take your wavelength, which would be the 4L thing, and then you multiply it by your frequency of the fork, the tuning fork, which you just read off the tuning fork. And that would give you a speed of sound. So roughly 343 meters per second. I say roughly because it's going to depend on your temperature in your room. You had to calculate your temperature, or figure out what your temperature is, because you have a speed of sound that actually changes due to temperature. And the equation that we have for that is velocity is equal to 331 plus 0.6 times your temperature in Celsius. So basically at 0 degrees Celsius, the speed is 331 meters per second. But at room temperature, it's pretty close to 343, so you'll have to figure out what your theoretical, then this would be theoretical velocity is. And using this would be your experimental. Okay, that's your experimental up here. So that's your next step, is to figure out your theoretical and your experimental speed of sounds for your data, and then calculate a percent error. So I'm going to have the substitute pause the video here, and we'll continue on with the explanation, taking a look at those questions here in just a few minutes. So take 5 to 7 minutes to get that calculation done if you haven't already done it. All right, pause the video. All right, I'm back. So let's start taking a look at some of these conclusion questions. Hopefully you were able to get some good data, but let's take a look at the first conclusion question. So the conclusion question is about the speed of sound and how it changes with frequency. So we saw that an equation for the velocity, the speed of sound, was that 331 plus 0.6 times the temperature in Celsius. So according to this equation, the speed of sound is temperature dependent, right? So it depends only on temperature. So then if the speed of sound is only dependent on temperature, then what should be the effect if we change the frequency? So if we chose two different frequencies in your experiment, should you see a difference? So the answer to that hopefully would be no, that there is no discernible difference between the speed of sound depending on the two different frequencies. We do know that speed of a wave is dependent on the frequency, right? At least according to this equation. If the frequency is going to go up, then shouldn't that affect the velocity? Well, it turns out that it doesn't. So if the frequency goes up, then the wavelength goes down. So you had to move the pipe around in order to figure out the place where this whole thing is going to resonate. So our velocity is equal to frequency times wavelength, but the velocity is the thing that's constant. And if the frequency goes up, then the wavelength goes down. Those are inversely related. So hopefully your data showed this. And the equation does say cite your data, so you want to make sure that you go back and actually say, okay, well, the percent errors were pretty low on both of them, so therefore they were pretty close to the same value. All right, what about the second one? So the second one says what happens to the speed of sound as the temperature increases. So we were just really talking about that. So you can say velocity is equal to, that should be the equal sign, equal to, there we go, 331 plus the 0.6 times the temperature in Celsius, and all of that is the equation for the speed of sound. So if the temperature goes up, what should happen to the speed of sound? Well, it should go up as well. So why? Why physically will that happen? Well, imagine dominoes, okay, dominoes. So if the dominoes are spaced like this, my dominoes keep getting wider. Okay, so dominoes like this. So if you were to knock this domino down, it would have to fall. And while it fell, it would eventually come and hit this next domino really low, right? And then this one would fall, and it would come and hit this one. So it would have to wait until it got all the way down here in order to hit the next domino. So there's a certain speed that is associated with this one. We'll call this one V1. Okay, then what happens if we take these same dominoes and we have a whole lot more of them, but we are putting them much closer to each other? Okay, so now if one starts to fall, all it has to do is hit the next one, which is very close to it, which hits the next one, the next one, the next one, the next one, the next one. And this would be have an effective speed, and it would be, we'll call that V2. So how would you characterize V2 versus V1? Which one would take, which one would have a higher speed? Well, hopefully you'll see that V2 is the one that's going to have the higher speed, because these dominoes are really, really close to each other. So why am I talking about dominoes when we were just talking about the speed of sound? Well, the way that sound travels through air, if we go all the way back over here to this thing, right, it's this particle hitting against the next particle, which hits against the next particle, and so forth. So they're like dominoes. So if the dominoes are really close to each other, then the speed of sound will be really, really fast. If the dominoes are really far apart from each other, then they are going to be pretty slow. So there's a couple things that go on with gas when you increase the temperature. So that when you increase the temperature, the molecules start moving around a whole lot faster, just in general, which actually makes the whole thing a little bit less dense. But since they're moving around faster, then we're going to be in a situation like this, where because they're all going in random directions and they're moving very fast, no one particle is very far away from another particle. And since they are traveling very fast, they're going to be able to transfer their energy to the next particle very, very quickly. So why is it temperature dependent? Well, it's all about how those molecules are going to be interacting with each other. And if the velocity is faster in the molecules of the gas, then the speed of the wave that travels through them is going to be much, much faster. All right, let's take a look at number 3. So number 3 says, why would the two values be different? So there's a weird thing that happens when we have a column of air. So let's go back to our PVC pipe here. So it's closed off at one end, right? And our waveform, our standing wave, looks something like this, right? So it's the quarter of a wavelength here, right? So we have particles that are not moving down here; they're just kind of hanging out, and we have particles that are moving really, really fast and going back and forth, back and forth, back and forth. Okay, but here is my question to you. If we were to blow up this area right here, so let's blow that up into a much larger scale here, okay? So we have the top of the pipe, and we have all of these little molecules that are right here at the very end, or the very edge of the pipe. Would you expect that they would just not cross this barrier, the top of the pipe? Okay, would the molecules, they'd just be going back and forth, back and forth, back and forth, but would never actually leave the pipe itself. So hopefully you'd see that that's kind of illogical to think. So of course we'll have oscillating particles going back and forth, back and forth, back and forth, but they might actually extend further beyond where the edge of the pipe is. So if that's the case, you measured the length of the pipe to be from the water all the way to the edge of the PVC pipe, when that's not entirely true. The length of the resonating column includes a little small part of air right above the PVC pipe that also is going to vibrate as well. So this full thing, let's do that in a different color. So this full part right here should have been the length of the air column. So if we did our wavelength to be 4 times the length of that air column, and our length was a little too small, that's going to make our wavelength a little too small. And if we then went to our velocity and said that that was frequency times wavelength, then we were pretty sure that our frequency was dead on because we're using these tuning forks, then the wavelength was a little small, which makes our velocity a little small. Now, of course, these tuning forks are old, and so they could possibly have been hit around a little bit and clanged, and so the frequency might not have been very accurate as well. But this right here is going to be the leading cause of some of your error. Okay. So if we take a look at the fourth question, it says, for the first tuning fork you used, calculate what length of the tube would have to be above the surface of the water to hear a column of air vibrating at the third harmonic. Okay, so we have to figure out what's going on with harmonics. And so we're going to have to take a break from the lab for a second and take a look at a few of our notes. So these notes are going to be called Standing Waves Part 2, or the Physics of Music, so we're going to go back to here. So that we are still talking about the physics of music. We were talking about strings and violins and guitars and anything that does anything with strings, harps, pianos even, although they're a little bit different in terms of how they hit the string. But today we're going to talk about pipes. So different pipes would be instruments such as clarinets, oboes, saxophones, tubas, any of the woodwinds, any of the brass. So this is all instruments along those lines. So we have two different types. We have the open pipe, and this is going to be more like, and I've never played any of these instruments, and so I'm taking the word from other people, a clarinet. So a clarinet. So a clarinet, I believe you play by blowing over an opening in the tube itself, which means that technically it's open at both ends. Piccolo would be the same thing. So remember that these diagrams here are not necessarily talking about a sine wave kind of motion inside the pipe itself. What we're talking about, excuse me, is how the particles move. Such like here, a node means that the particles don't move at all, while here that means the particles are going to be vibrating very, very quickly. Okay, back and forth at the most that they can have. So remember we have nodes, and we have this thing called an antinode. So the thing about open pipes is that they have to have an antinode at both ends. So in order to have an antinode at both ends, then you're going to have a node in the middle, and so this would be considered our fundamental, our first harmonic. Now if you looked at this, you would see, okay, well, this right here looked like the one thing we were looking at in the lab, and then this is another one of those. So if we were to put those together, but in a different order, you would see that they would form one of these, which we saw before is half of a wavelength. So here we have half of a wavelength, while here we have a full wavelength. So if we do 2 over 2 wavelengths, right? Here we would have a full wavelength plus another half, so this would be 3 halves of a wavelength. Then we have 4 halves of a wavelength, and you can see where I'm going, right? 5 halves of a wavelength right here, all on the same length of pipe. So our wavelength here would be, if 1/2 lambda equals L, then lambda would equal 2 over 1 L. Okay, that's a really weird L. Or it would be 2 over 2L, or 3 over 2L, or let's make sure I get this right, since I screwed it up last time. So the next one would be 2 over 2L, of course. the next one would be 2 over 3L. So the equation that we would have then for all of these, if we are looking at the basic equation, is lambda is equal to 2 over 2L. Let's do it that way, 2L over N. So that means that our velocity equation for something like this, remember that velocity is equal to frequency times wavelength, and we would have that the velocity is equal to the frequency, so F2L over N, or that the frequency that produces a resonance or produces a harmonic on a given length of pipe is equal to NV over 2L, which you might remember is the exact same equation that we had for strings. It's the exact same one that we had for strings. All right. So again, we have first harmonic, second harmonic, third harmonic, yada, yada, yada. And keep on going. We have something different when it comes to closed pipes. Okay, here are the first three harmonics for the closed pipes. Notice how things get a little bit different with the numbers that we have. First, third, fifth. What are we missing? We're missing any of the even ones. The second one is not there. The fourth one is not there. So what's going on? Well, since we have to have an antinode at this end, and we have to have a node at this end, then that means we are required to use certain waveforms that only show up as parts of quarters. So this one is 1/4 of a wavelength. So we have half a wavelength here, and then 1/4 of a wavelength here. So that means we have 3/4 of a wavelength. And then we have a full wavelength here, and then we have another quarter. So that means that we have 5/4 of a wavelength. So if all this happens on the same length, then that means that our lambda would be, in this case, 4L over N. And then our frequency equation would, by the same thing as what we did last time, would be NV over 4L. But we have to be very careful. N can only be odd. Okay. Now you could throw in an even one in there. You could do 2V over 4L and get a number. But that number is not going to have any physical significance. It's not going to work in any pipe that you try to do it because of this nature of having a node at one end and an antinode at the other end. So these frequencies would be the frequencies that produce harmonics on a pipe. So NV over 4L. Now, with this whole 4 that's showing up in here, that's kind of like our lab, right? And this right here looks like the waveform that we have in our lab. We have a node at one end because it's closed off by the pipe, and we have a fourth of a wavelength that shows up when we have an antinode at the other end. So this is exactly what we were doing in the lab. So taking a look here, right, we have open at both ends. We have 1, 2, 3, 4, 5, right? These are our harmonics. But here we have 1, 3, 5, 7, 9. So we don't have any of the even harmonics on a pipe that's closed at one end, or we call them closed pipes. So just keep that in mind. We have to make sure that if we're using an equation, we can't use an even when it's not going to exist. One of the things that sometimes gets said is we have this thing, and if you've ever heard this, if you're musically inclined, you might have heard this, overtones. Right, overtones. So this would be the first overtone, meaning that's the first one that's available over the fundamental. And then we would have second overtone, third overtone. But those start getting a little confusing if we start thinking about it like that. Why don't we just keep it with the evens don't exist on a pipe that's closed at one end. So let's take a look at a sample problem. Closed pipe, so that's very important now. Closed pipe, which is 0.5 meters long, is used to produce the first three harmonics. What are the frequencies if the speed of sound is 340 meters per second? So we're in our equation, frequency is equal to NV over 4L. So the first harmonic would just be V over 4L, and that would be 340 multiplied by 4 times 0.5 meters. So 4 times 0.5, that just gives you 2, so it's half of 340, which half of 300 is 150, half of 40 is 20, so this should be 170 hertz. Hopefully I did my math right. I'm not planning on checking that. Yeah, that makes sense. Okay, so that's for the first, right? So let's talk about the next one. First three harmonics. Well, that's telling us not to say that we're going to do the second harmonic and the third harmonic because the second one doesn't actually exist. So the third harmonic would be 340 times 3 over 4 times 0.5, or just 3 times this number that we have right here. So it works the exact same way that we had for strings, where the next harmonic is an integer multiple of the fundamental. We just have to remember that closed pipes, we can't use any of the even integers. So what's 170 times 3? So that would be 510, right? 3 times 7 is 21. 3 times 1 is, or 10, I guess, is 30. So it would be 30 and 21, and then, of course, we have that extra 0. And then the last one would be the fifth harmonic, and I'll leave you to figure that one out. But if we go back to our lab, right, question number 4 on our lab says that for the first tuning fork you used, calculate what length of tube would have to be above the surface of the water to hear a column of air vibrating at the third harmonic. So our frequency would be NV over 4L, right? So you had to have the frequency, whatever frequency you chose to use, NV over 4L. Then we're actually calculating length, right? So L would be NV over 4F. Now what N are we using? So this is the third harmonic, so that would be N is equal to 3. So our L would be equal to 3 times, now you would use the speed of sound that you calculated, so we'll use the experimental version because that's what you actually figured out in your setup, divided by 4 times whatever frequency you used for that tuning fork, and that's how you get that one. All right, so we are at the end, so you'll be handed some practice problems as well as a few other things, I think, to help practice some of these things. So you'll have the rest of the class to work on it. And if you haven't looked yet, there is Mastering Physics that you should be working on. So make sure that you are taking a look at that as well. And I will be back come next week. So if you have any questions, you can always find Ms. Rittenhouse, or you can come talk to me next week. All right. Hope you had a good one.